Welcome to Seismic Sound Off, exploring the depth and usefulness of geophysics for the scientific community and the public. I'm your host, Andrew Geary. As the size and complexity of data soars exponentially, machine learning has gained prominence in applications in geoscience and related fields. Machine learning-powered technology increasingly rivals or surpasses human performance and fuels a large range of leading-edge research. In this conversation, Herman Jaramillo discusses his new book, Machine Learning for Science and Engineering, Volume 1, Fundamentals. This book teaches the underlying mathematics, terminology, and programmatic skills to implement, test, and apply machine learning to real-world problems. In this episode, Herman explains why this book is a unique contribution to machine learning, the role of intuition in using machine learning, and what's in this book that you rarely find in other books on the topic. He also goes in depth on the critical understanding of finding the best suited algorithm. This conversation and book explores the hottest topics facing students, scientists, and engineers. And this episode will provide a solid foundation to understand how to utilize this cutting-edge science in your own work. To find the links to buy this fundamental book on machine learning, visit seg.org/podcast or check out the episode's show notes where you're listening. And now, my conversation with Herman Jaramillo. Well, speaking of increasing that knowledge, you have a new book that you serve as a co-author, and it's called Machine Learning for Science and Engineering, Volume 1, Fundamentals. I'm going to start with a question you ask in the foreword of the book. Why do we need another book on machine learning?
Well, there are many books out there on machine learning. However, some of them are too theoretical and some just too practical. That is, to focus to programming details. We wanted to fill the gap between the theoretical and the practical issues. The book has some fundamentals in linear algebra, which set up the theoretical basis for the development of machine learning. In addition, we address a few techniques of machine learning with good theoretical support, such as linear regression, logistic regression, artificial neural networks, support vector machines, etc. We provide practical examples and code both in MATLAB and Python, which the reader can implement easily in his or her own computer.
You're kind of answering it there. What would you say is the main teaching objective in this book?
Well, many people get great skills at using software, which that's machine learning. However, not many understand what is behind the programs. This book not only uses programs to illustrate the main ideas behind machine learning, but it shows the mathematical basis so that the programs are not used as black boxes. The main teaching idea here is to understand their theoretical basis and to be able to use them to implement practical programs.
What would you say is the importance of intuition for scientists and engineers using machine learning to solve some of their challenges?
That's a very interesting question. Well, intuition is not only important in machine learning, but in any field of science. The development of formal theories require a great deal of effort, skills, and knowledge. But the intuition let us have a good judgment over what could be true and what could not be true. Good intuition can save us a great deal of work by indicating the path we should take to solve a problem. This is true not only in general, but in the field of machine learning. Intuition and fundamental theoretical understanding are crucial when working with real data. Real data has unique challenges, and algorithms and workflows have to be tweaked to deal with this. Without the fundamental insights, this is hard or impossible. Also, there is an issue of missing or bad data. We discussed this at length in our book, as we know how important it is for science and geophysics in particular.
Yeah, that makes a lot of sense considering the data is one of the key inputs when you're using machine learning. Could you explain the topic of the pseudo inverse and how you set out to discuss this particular topic in the book?
The topic of pseudo inverse is a great topic. In our careers, we spend lots of time discussing and finding the inverse of operators. Operators for us in the finite dimensional space are matrices. There's something more general in functional analysis. Operators are necessary to simulate or model synthetic data. However, in practice, the percentage of operators which actually have an inverse is nearly zero. It is much more common to find non-invertible operators than invertible operators. Of all possible operators, statistically, the probability of hitting an operator which has an inverse is zero. The pseudo-inverse is the best inverse of a non-invertible operator. Now, what does it mean best? The best means that the solution of the equation using the pseudo-inverse presents the smallest in the least square sense. And that solution is also the smallest solution. By error here, we mean the difference between the known data and the synthetic data produced by the operator. A practical example is that of linear regression. We can write a linear regression problem as the matrix times a vector equal to some data. We do not know the vector that optimizes the problem so that this vector produces new good data. The matrix does not have in general an inverse. The ideal vector, which is what machine learning is about getting these magic parameters on this vector, is obtained by the product of the pseudo-inverse with the data. Then, with this new vector, we can generate good new data. Learning means to learn this vector.
You explained very concisely and clearly the value of this book, why you thought another book on machine learning was helpful. And I want to go a little into more detail about something you talk about in the book, linear conjugate gradient method. Why did you think it was important to go into more detail on this topic compared to other books on machine learning?
Well, actually, the linear gradient, I have an appendix. We have an appendix on the book. But linear conjugate gradient is the best. Best means fast and precise method to solve a linear problem for huge sparse matrices. There is no other method that would beat the linear gradient. The linear problem is still a problem of great importance today and will always be there in the future.
You introduce readers to deep learning architectures in this book. What about this technique excites you?
Well, deep learning architectures are very exciting. For example, CNN, which means convolutional neural networks, are great to work with images. We can never underestimate the importance of interpreting images for all branches of science and engineering. Another great network is that of natural language processing. This subject is becoming more and more important every day with the many tools to communicate between machines and people today.
Why do you see as one of the goals of this book to help with finding the best suited algorithm?
The question of the best suited algorithm is a hard question to answer. But we need many issues here. We have to solve many issues. Let me just list a few. We need to understand the problem. That is why the theory developed is useful. The theory is focused toward understanding the problems in machine learning. We need to understand the data. To understand the problem is not sufficient to understand the theory, but also to know and be able to understand the data, to interpret the data. This in terms of format, size, features, structure, etc. In this study of the data, we need to get insight into the distribution patterns, missing values, outliers, potential relationship between variables, etc. We showed in the book some insights into this in the techniques of regression, principal component analysis, outlier detection. etc. We need to define performance metrics. We should be able to judge the performance of the algorithm. We also should consider the algorithm based on the type of problem that needs to be solved and the data available. Here we should think of supervised learning or unsupervised learning or semi-supervised learning or reinforcement learning. Finally, based on the type of the algorithm, you should decide on the algorithm options to use. For example, linear regression or logistic regression, k-nearest neighbor, artificial neural networks, PCA, etc. You need to assess the algorithm suitability, considering things like data size, interpretability, computational resources, time complexity, robustness, noise outliers, regularization, and hyperparameters. You can also consider to iterate and refine your models using different pre-processing techniques, feature analysis, etc.
Yeah, that's a very helpful and thorough response there. That topic, I'm sure, fills up many machine learning books. That's really one of the big points of finding the best suited algorithm. What is an overlooked assumption of the k-means method?
Well, there are many, actually. There are many overlooked assumptions on the k-means method. First, we need to predefine the number of clusters. That's one. Now, k-means forfeiting of the data, you assume some kind of spherical clusters. This can be intuitively explained by the Euclidean distance-based objective functions. The boundaries between clusters should be convex. That's another assumption. And the final assumption here is that k-means assume that all clusters have similar variance and standard deviation. That is, the clusters are isotropic. To overcome these limitations, there are options like something called the kernel trick, which we discuss extensively in the book. And other methods are dbScan and HDBScan methods, which are also explained in the book. dbScan is density-based methods, and HDBScan are using hierarchies and density too.
What is the importance of principal component analysis?
In principal component analysis, we should consider two important points. One point is dimensionality reduction, and the other is data compression, which somehow are related. But let me explain a little bit about dimensionality reduction. In dimensionality reduction, we can reduce the dimension of the data for several reasons. One reason is to save memory or to speed up process, and also for interpretability. That is, if you have, for example, 13 dimensions and you drop that into 2 dimensions, then you can graphic in a Cartesian plane the data on those 2 dimensions and give an interpretation of it. So it's very important. In the side of data compression, we show in the book an example of data compression. You have an image, for example, and the image has many colors, and you can reduce some colors which are not very important in the image, and then compress the data, reduce the size, let's say from 100 megabytes to 2 megabytes or 3 megabytes, and you still can see the image very well. So that is an example of data compression that you can achieve using principal component analysis.
What else will the reader find in this book that is rarely, if ever, explicitly included in machine learning books?
I have several points to talk about here. One is the section of in linear algebra is fundamental and well explained, very well explained, with emphasis in regularization, the pseudo-inverse, and the fundamental theorems of spectral decomposition and singular value decomposition. Now, some examples are specialized to geophysical problems not found elsewhere. Another point is that the style of explaining the theory from fundamental concepts up to the developing exercise which illustrates the theory is unique. This style comes from the interplay of Andreas Ruger, who is a geophysicist, and myself, who I'm a mathematician. So I can bring the theoretical part and a little bit of the rigor but Andreas put the things back to earth with his practical point of view.
Herman, what do you hope this book achieves?
I think this book is a complete textbook for either a class on machine learning or for self-study. And that's my main achievement on this book.
Why was creating this resource on machine learning for students, scientists, and engineers, maybe even mathematicians, important to you?
I think it is important to me because the unique way in which the topics are introduced, explained, and exercised. It has plenty of fundamental theoretical and practical development with mathematical and graphical illustrations.
Well, AI has to be one of the hottest topics in the world right now. So what one thing would you want to make sure that a scientist or engineer takes away from this conversation and how it relates to their day-to-day work?
I hope that a scientist or engineer will see that machine learning has firm basis on fundamental mathematical principles, and with the help of programming tools can make into the reality that we are seeing today. I believe that every professor has their own unique style. My style is to illustrate the concepts from different points of view. The concept is the intersection of all viewpoints. We need to enforce intuition and formalism. The formalism is important to write ideas as equations or as programming code as organized as possible. The intuition can help us to identify good directions and guide us into what seems correct and what does not. I use both intuition and formalism in my lectures. I use graphics every time I can. While a graphic is not a formal mathematical proof, can be of great didactic help.
And lastly here, what principle, teaching, or point of view has helped you succeed in your field?
Well, actually, it's the principle of being practical and theoretical too. I have to acknowledge that I am a pure mathematician, but because I went into the field of geophysics, I learned a lot of practical things. And I'm working with Andreas, who is a very practical person, taught me also to be practical and working on programming. So the combination of both theory and practice is ideal. And the field of machine learning is an excellent point when you can use all this theoretical background and use the practical and the computational skills to merge them together and to create great products.
Well, I appreciate you sharing that. I had the privilege a few years back to visit Medellin for a long weekend and really had a great visit there and really enjoyed my time. So I appreciate you talking about this new book and for publishing it with the SEG, and excited to share this with our audience.
Thank you so much.
You reached the end of Seismic Sound Off. Thank you for listening to this episode. If you want to be the first to know about the next episode, please follow or subscribe to the podcast wherever you listen to podcasts. Two of my favorites are Apple Podcasts and Spotify. If you have episode ideas, feedback for the show, or want to sponsor a future episode, visit seg.org/podcast and find the box titled Contact Seismic Sound Off. Zach Bridges created original music for this show. This episode was hosted, edited, and produced by me, Andrew Geary at Treasurement. The SEG podcast team is Jennifer Cobb, Kathy Gamble, and Allie McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.